Hello. In this video, we are going to investigate polynomial functions of higher degrees. Polynomial functions. Several characteristics include they are continuous, meaning you can draw the polynomial graph without picking up your pencil. They have no breaks, no sharp or pointed turns, smooth and rounded. So pretty much you've already looked at a quadratic function prior to this. Well, a polynomial function is going to be very similar, just maybe some more turns and curves, but it's going to continue to be smooth. So let's look at a polynomial. F of x equals x to the fifth. This function has a power of 5, hence a higher degree. Let's graph it. Our end behaviors are going to be opposite, but because it's odd, but because our coefficient is 1 and it's positive, it's going to end going in the positive direction. So that's x to the fifth. Now we can apply transformations just like we have in the past. If we make it a negative x to the fifth, it is going to reflect across the x-axis, just like that. What if we add 2 to the function? It's going to move up 2. What if we subtract 3 from the inside? It's going to move right 3. Now let's look at another function. So the previous function was x to the fifth. This function is x to the fourth. Let's graph it. This one's very similar to x squared with the fact that its degree is an even power. There we go. It's very similar, it's just a little bit sharper than your x squared. So what happens if we add 1 to the outside? It moves it up 1, right? What if we add 1 to the inside? It moves it left 1. Lastly, what if we say 1 minus x to the fourth? Well, that flips it down because the x is negative, but our 1 is positive, so it moves it up. Leading term test. Let's see what this means. So we had f of x equals x to the fourth, and it looked like this. We had f of x equals x to the fifth, and it looked like this. Let's see what we notice. On x to the fourth, both ends are going up, right? And x to the fifth, the ends are opposite. Well, what happens if we compare 4 and 5? 4 is even, 5 is odd. So whenever we have an even power, our ends are going to go in the same direction. When we have an odd power, our ends are going to go in opposite directions. Okay, in this case, let's compare f of x equals x to the fourth and f of x equals negative x to the fourth. Here we have a positive 1 as our leading coefficient. F of x equals negative x to the fourth, we have a negative 1 as our leading coefficient. When we have a positive leading coefficient, our function is going to open up or end up. When we have a negative leading coefficient, our function is going to end down or opening down. So let's have a great flow chart to help us. First, we have to determine, is our function odd or even? Then from there, if it's odd, we have to decide if it's positive or if it's negative. If it's odd and it's positive, it's going to have opposite ends, and it's going to end going to infinity. If it's negative, they're going to have opposite ends, but it's going to end going to negative infinity. That means the right side of the function, if it's positive, the right side of the function is going to go to positive infinity. And if it's negative, the right side of the function is going to go to negative infinity. Well, if it's even and it's positive, or if it's negative, if it's even and it's positive, it's going to go to infinity both ends. Ends go in the same direction. If it's negative, we're going to have same ends, but they're going to go in negative infinity, the negative direction. They're going to open down. So we're going to use the leading term test to determine the end behavior of the function. F of x equals 16x to the fourth minus 2x plus 7. So the way we state end behavior is as x approaches negative infinity, f of x approaches. And we have to decide, is it going to approach infinity or negative infinity? Meaning, on the negative side of our graph, as x approaches negative infinity, the negative side, the left-hand side of our graph, where does our end behavior go? Does it go up or does it go down? And the same idea on the right hand of the graph, as x approaches infinity, okay? The positive side of the graph, the right-hand side, does our end behavior, does it end going up or down? If it ends going up, it'll be positive infinity. If it ends going down, it'll be negative infinity. So here's our flow chart from the other page. First thing we have to decide, is this function odd or even? Well, our power is 4. Is 4 an odd or even number? It's even. So we can take away the other flow chart. We don't need it. Now we have to decide, is it positive or negative? Well, we have 16. Is 16 a positive or negative number? It's positive. So we know that we're going to have the same ends and they're both going to go to infinity. So as x approaches negative infinity, f of x approaches infinity. And as x approaches infinity, f of x approaches infinity as well. So on the negative side and on the positive side, so on the left side and the right side, both ends are going up. Real zeros of polynomials. Another word for zero is solution, right? So let's look at the following statements. They all mean the same thing. They're just different ways of saying it. X equals a number, a, okay, a just represents any number, is a zero of the function. Meaning it's a solution, it's an answer, it's a root, right? X equals a is a solution of the function. Same thing. X minus a is a factor of the function. And a comma 0 is an x-intercept of the function. All four of those statements mean the same thing. All four of those tell me that a, if I take a and I plug it into this function, it's going to make the function equal 0, meaning it is a solution for the function. So let's find the real zeros of the function. F of x equals 2x to the fifth minus 6x to the fourth plus 4x cubed. Now we're going to have to factor this. So over here on the right hand of your screen, I have brought over the factoring process from Algebra 2 Trig. Remember, we wrote this on a note card. So the first thing we have to do is check for a GCF. We have 2x to the fifth minus 6x to the fourth plus 4x cubed. Do we have a GCF? Yes, we do. 2x cubed. So that means we can divide all three terms by 2x cubed. So f of x, now we're factoring out 2x cubed, so it needs to go in the front. 2x to the fifth divided by 2x cubed is x squared. Negative 6x to the fourth divided by 2x cubed. Negative 6 divided by 2 is a negative 3. 4 minus 3 is 1. Oh, oops, that was supposed to say 1. Negative 3x. Ignore that squared. Ignore the squared behind the 3x. All right, 4 divided by 2 is 2, and x cubed divided by x cubed is, x is 0, which is 1. So we have plus 2. So now we have to factor this. Okay, so we've checked for our GCF, we've factored it out. Now we have to multiply our a and our c. A is 1, c is 2. So 1 times 2 is 2. Well, we know that the only factors of 2 are 1 and 2. So how can we combine these to equal b? Well, we either have to add or subtract them. Well, we want to be negative 3. So a negative 1 minus 2 equals negative 3. So we found the factors that add or subtract to equal b. Step 4 tells us that we have to put both of these factors over ax and reduce. Our a is 1, so 1x. Negative 1 over 1x and negative 2 over 1x are as reduced as possible. So now we have to fill in our parentheses. F of x equals 2x cubed, and then there's our two sets of parentheses. Remember, bottoms up to fill in the parentheses. So our bottoms are 1x, so I slid those up, and then our negative 1 and our minus 2. So now we have filled in our parentheses. So that was a step to factoring. Now we actually have to solve. So we have to take all three of these and set them equal to 0. Do not forget about the 2x cubed in the front. 2x cubed equals 0, negative x minus 1 equals 0, Oh, goodness gracious. Why do I have negatives in front of there? Y'all, I guess I was just getting really happy. Those negatives are not supposed to be there. Okay, the negatives are not supposed to be there. It's supposed to be x minus 1 and x minus 2. First, let's solve 2x cubed. Well, we have to divide both sides by 2, which is 0. And then we have to cube root, which is 0. Now, because it was an x cubed, this has, oh, goodness gracious, this has a multiplicity of 3. All kinds of things are happening on this slide that weren't supposed to happen. So, negative x equals 1. That is incorrect. It should say x equals 1 because we would have added 1 to both sides. And then negative x equals 2 should just say x equals 2 because we would have added 2 on both sides. And then ignore the x equals negative 1 and the x equals negative 2. So we knew because of this polynomial function that we were supposed to have 5 roots because that was the degree. So we have x equals 0 and it has a multiplicity of 3, so that counts for 3 roots. Then we have x equals 1 and then we have x equals 2. So be sure that you correct that if you're taking notes. Do not write it the way it is on the screen because I made a big old fat mistake. I'm sorry, guys. Okay, if y'all didn't know I was human, there you go. There's a prime example of how I'm human. All right, let's talk about the intermediate value theorem. This is a whole lot of words, but I'm going to break it down for you. So it says, let A and B be real numbers such that A is less than B. If f is a polynomial function such that f of A does not equal f of B, then in the interval AB, f takes on every value between f of A and f of B. Oh my goodness, what does that mean? What's a good thing you have me to tell you? So first of all, this helps us find zeros of polynomial functions. Okay, it helps narrow down the window of where we're searching. First step, your equation must equal 0. If we're going to solve a function, it has to equal 0. Second, we're going to have 2 numbers from our interval A and B. Okay, I'll show you an example. You're going to take both of those numbers and plug it into the function, and that will tell you what f of A and what f of B is. Then we're going to compare f of A and f of B. We're going to say is one positive and is the other negative. We're going to look at that. Yes, then there's a 0 between A and B. No, then there's not a 0 between A and B. Well, then there's most likely not a 0. So let's look at an example and see what all of that meant. Does the function have a 0 on the given interval? Well, I gave you the function x cubed minus 5x squared plus 5x plus 8 equals 2x plus 3. The interval is 1, 2. Here are our steps from the other side. First, our equation must equal 0. Well, right now our equation equals 2x plus 3. So I need to subtract 2x from both sides and I need to subtract 3 from both sides. Once I do that, I get x cubed minus 5x squared plus 3x plus 5 equals 0. I need to plug in A and B. What are our A and B? A is 1, B is 2. So we need to plug in f of 1. F of 1 equals 1 cubed minus 5 times 1 squared plus 3 times 1 plus 5. That is going to simplify to 4. Now I need to plug in f of b, which is 2. So whenever I plug in 2, I get 2 cubed minus 5 times 2 squared plus 3 times 2 plus 5. Whenever I simplify all that, I get a negative 1. So now we've plugged in a and b. Our next step is to compare f of a and f of b. F of a is 4. F of b is negative 1. 4 is positive, negative 1 is negative, right? Okay, I needed one answer to be positive and one answer to be negative. So, since 1 is positive and 1 is negative, I know that there is a 0 on the interval 1, 2. There is a 0 in between there because I had to cross the x-axis to go from 4 to negative 1. Let's see what this looks like. Oh, before I move on, x cubed. It tells us that there should be 3 solutions, right? Okay, well, we know where 1 is located. It's in between 1 and 2. So, in a second video, I'm going to show you how to analyze the graph to determine where the other intervals are located. But that is all for this video. Be sure to tune into the second video to see how to analyze the graph.